Okay, today is September 24th, 2025. And last time we were talking about the components of a vector, Cartesian components of a vector. And that's a much more straightforward way of summing vectors, summing and subtracting vectors, right? So, and let's just summarize here. The components, the Cartesian components of a vector can be written down as you go. We have this one. I wanted the A vector. Here you go. That's the one I want. Can be written down as the x component of a vector plus the y component of the vector. And this vector that has x and y components can be here written as its scalar component times the unit vector along the x direction. Again, the scalar component of the vector, the component of the scalar value of the vector in the y direction times y hat. But to be more generic, we can also put a z component right in here. And z component right in here. Okay? And the magnitude of this vector is just given by all the components are perpendicular to each other. The magnitude of this vector, I'm going to put the square, okay? The square of the magnitude of this vector can be written down in terms of the square value of each scalar component. The sum of the square value of each scalar component. Like that. And if you're summing vectors, A with B, for instance, right? If you're summing vectors A with B, all you can do is to sum their components. The components are summed up regularly, like regular numbers, but only the components. Okay, you cannot sum the components of the x with the y, right? But only the components with the same, only the factors with the same components, like that. And similarly, by the same token that I did something like that, I can also do something like that, right? The square, the magnitude, the square of the magnitude of A plus B vector is going to be given by the square of this one, the square of this one, and the square of this one. Okay? And then all you gotta do is to apply those formulas for some specific numeric problem like we did before. Okay? So going back to the topics that we have covered so far, Okay, chapter 1. We cover the components of a vector. We cover the addition of vector by means of the components. Okay, we did that. Rather straightforward way. And now we want to cover two-dimensional motion. And let's take a look at the book as well. Wiley plus. Logging. Launch the textbook. And let's take a look here at the kinematics in one dimension, right? We finished kinematics in one dimension. And now we're going to start kinematics in two dimension. That's what you're going to do now. Here are my notes. Let's see if I have to show you anything else. Okay, so vectors A and B, I showed that before, right? So here you go. Here I'm just displaying the components of the vectors ax, ay, bx, by, right? We can sum the components of those two different vectors and obtain a final vector that's going to be this, that will have this component here plus this other component. Would be nice. Let me see if it would be nice to display the resulting component. Here you go. I'm going. And this other one. Like that. And I'm going to draw the resulting vector. That's going to be the resulting vector here. Okay, and that's going to have a different angle, right? Not necessarily, it's not going to be necessarily the same angle for the A or the B, but it's going to be, most of the time, it's going to be at a different angle. Okay. We have more stuff here. We go three-dimensional representation. Yeah. Here's the three-dimensional representation of the vector, the vector, right? And one important, how do you orient, right? The question that you may ask, how do we orient those axes, X, Y, and Z? right? Very important. That's something that they don't tell you for some reason. People don't tell you. You have to figure out by yourself. You orient, which direction is going to be the positive, right? With positive and negative axis with respect to each other, right? Oh, the way we orient those axes is just by doing the right hand rule. You have to do the right hand rule from X to Y. Your thumb points the Z direction. Then you do Y cross Y to Z. Y to Z points in the positive X direction, and Z curling, right? To curling your palm of your hand towards the X points in the direction of the Y axis. Okay, the positive Y axis. And let's write that down. We call that the right hand rule. Okay, for a three-dimensional X, Y, Z axis, the orientation of each one of those are given by the right hand rule. Okay? So it goes like that. One, in order to find out the proper direction of the z-axis, you must curl the palm of your right hand from the x-axis to the y-axis. And your thumb will point in the direction of the z-axis. Okay? Then you repeat, for the direction of the x-axis, you repeat the above for the y-z axis. Okay, curl. Here you go. Okay. You must, let's put it this way. You must curl your right hand from the y-axis towards the z-axis. Okay? And your thumb will point in the direction of the x-axis. Okay, and always in this order: x, y, z, x, y, z. Always, that's what we call cyclical order. For the proper direction of the y-axis, you must curl. Let me see if I did it right. Oh, I didn't do it right. For the proper direction of the x-axis, you must curl x. Okay. From the y-axis toward the z-axis. Okay. For the proper direction of the y-axis, you must curl the palm of your hand from the axis towards the x-axis. And you get, you always use this order: x, y, z, y, z, x, and z, x, y. Okay? Curling from the x to the y, you get z. Curling your right hand from the y to the z, you get the x-axis, the direction of the positive x-axis. Curling the palm of your right hand from z to x, you get the direction of the y-axis. Okay? So that's how you determine the proper direction of the XYZ axis in the three-dimensional space. In the two-dimensional space doesn't, it doesn't matter, right? It doesn't matter because you have only two axes. You don't have to worry which direction those two alone should be. Only if you have to know the direction, only if you have to draw properly the three-dimensional axis that you have to do something like that. And now we are going to talk about two-dimensional motion. 2D motion. Now that we cover vectors, 2D motion. And I want to syllabus vectors 2 and 2D motion. 2D motion 1, let's put it this way. We do not need that. For the next class meeting, we are going, wow, time is going by quickly, huh? So the exam is already in 2 weeks. Okay, the exam is going to be ready in 2 weeks. Someone is trying to come in. Good. And let me get another. Here you go, 2D motion, genetic 2D motion graph. Okay. So in order for you, in order for you to describe the two-dimensional motion, you must have, first of all, you must have a x-axis, right? And because it's two-dimensional motion, you have to come up with a y-axis as well. And that's what we have here. The y-axis crosses the x-axis at the origin. And then you must label those axes. Notice that the unit that I put there is in meters, right? X in meters, Y in meters. That's because I am mapping the two-dimensional space. My object is going to move within this place, this plane. But just like I said before, we can also locate our object in the three-dimensional space. In order to locate our object in three-dimensional space, we have to draw the X, Y, and Z axis, right? And place your object somewhere in the X, Y, Z coordinates. X, Y, Z coordinates. And here we go. And now here we go. Here, let's say, suppose that your object is describing this path along this line. As time goes by, your object moves from here all the way up to here. Here is for, let's say, for t equal to 0, right? And here is for t equal to t final. From t initial to t final. I'm going to put my object in a given point along this path. Okay. And let's say I call this point, let's say I call the initial position of my object. Okay. Yeah, I'm gonna be more explicit here. Here you go. I'm gonna put right here, which is like I said before, it's my t equal to 0, right? My t, the position, the initial position of my object at t equal to 0. I'm going to adjust my graph, my vector position. Initial position. I don't need that anymore, right? And as time goes by, this vector position keep on changing. Okay, and I'm going to label here. That's going to be my instant of time t equal to t naught, equal to 0. I don't need that anymore. On the top of that, we have the coordinates x naught and y naught. Do you picture that? You got? Not only you can denote the vector position in terms of the initial vector position r naught, but you also can denote that in terms of the initial coordinate points, initial coordinate points, x naught, y naught. Okay. I don't need that anymore. And here we go. What else can we do? We can denote this initial vector position by this notation that you see. Oops, not here. By this notation that you see right in here. R naught is equal to x naught x hat plus y dot y hat. Okay? I don't need that. And then as the particle moves along this path, right? Here you go. As, oh, finally. I, I hate that. Oh, here you go. As this particle moves along this path, right? As time goes by, this particle is going to move along this path. Now I can grab it here. Yeah, like that. Just try to picture a movie playing in your head. That's no longer going to be T naught. It's going to be T something else, right? If that's your final position, okay, that's going to be your final position. Let's say TF. It's not going to be 0. Then that's going to be your final vector position. Your final vector position is going to be given by xf plus x hat plus yf y hat. And I'm going to denote that guy here by RF. And the points, the coordinate points, the Cartesian coordinates of this specific point is going to be xf yf. Like that. Okay, and then we do not need that. Let me put one more thing here, right? This TF is going to be greater than 0. Oops, greater, not less. Greater than 0. I prefer this head for the. And if I want, I can play, I can play a movie, right? Here you go. As time goes by, this position vector keep on changing, right? Keep on changing in time, right? That's what not only the particle is going to be at a different position along this path, but this vector position also is going to change as time goes by. Okay, and I don't need that. Let's see, I'm gonna need that. Yeah, I'm not gonna need that. And now we can come up also with something else that is the displacement. What about the displacement? How does it look like, right? Remember, we started in two-dimensional. Here you go. For 1D motion, we have the following definitions. One, position. Two, displacement. Three, average velocity. And I'm going to put speed. And in addition to displacement, I'm going to put the displacement distance traveled. Right? Instantaneous velocity slash speed. Instantaneous velocity slash instantaneous speed. Then we have what? Average acceleration and average and instantaneous acceleration. Instantaneous acceleration. For 2D motion, we have something similar. But it is just a little bit more complicated because we have to deal with vectors, right? Here you go. We have vector position. And then we have the vector displacement. And I'm going to illustrate my vector position. I already illustrated the vector position. I'm going to illustrate my vector displacement. Okay, and vector displacement, let's not forget, it is written down in the following way. Write our vector displacement as delta r. And delta r is going to be what? R final, just like we have in the one-dimensional space. R initial, okay? R final minus R initial, like that. And how does it look like in the two-dimensional space? R final looks just like that. And R initial looks just like that, okay? So I'm going to copy and paste here. Here you go. Here's my R final. And here is my R initial. Like that. And let me change the arrow, the head of my, yeah, I prefer this head here. And I gotta label it, right? Let's not forget to label it. Oops, R initial. I don't need that anymore. Oh yeah, let's use that. Let's use that. You know, I'm gonna write R naught, X naught, why not? Okay. And I can even put also the x naught and y naught there in the graph as well to make it complete, right? Here you go. I'm gonna put this guy right in here outside, and I'm gonna put this R naught right here inside. XF X naught, Y naught, YF. How does the displacement vector looks like? Do I need that? Yeah, I have to move this one. Good. And I want to show you how it looks like. The displacement vector is supposed to look like the following, mathematically speaking, right? The formula of the displacement vector is this one that you see right here. And I don't need that anymore. Let's increase the size so you can see it better. Yeah, that's how is the summation of two vectors. Is the summation of the RF vector with the minus R naught vector. The minus R naught vector. You got. So what we have to do, I have to invert the direction of this vector here. Right? And I have to relabel it. Instead of R naught, now it's going to be minus R naught, just like I did before, right? And connect the tail of the R naught to the head of the RF. We have the displacement vector. And I'm going to draw that in a different color. Let's put that in red. And I'll put that in red as well. Okay. And now that I put that in red, yeah, let's keep it here. That's my delta R vector. That's the genetic treatment for those two-dimensional definitions. We don't need that anymore. Right? Go. I don't need that anymore. Let's reshuffle. Let's play it again, right? Here you go. If I want to follow the path of an object in the two-dimensional space, the three-dimensional space is going to be more complicated, right? So we don't cover that. All you have to do is to come up with your x-axis. Put a better arrow there at the top, at the bottom. Here you go. And then this one here. X and Y axis. We draw a path for this object, and that's what the path is going to be. And between t equal to 0 and t equal to tf, the particle is going to be anywhere between this point here and this other point here, the extreme. Okay, here you go. Just making my slides look better. we can illustrate the initial position vector. Initial position vector, and we can also illustrate the final position vector. And I have it the right one. Here I'm illustrating both the final position vector and the initial position vector in the same graph. Okay, I don't need that anymore. And I am illustrating as well the displacement vector, which is given in terms of the R final plus the minus R naught vector. Notice that I changed the direction of the R naught vector right here. That's how we illustrate the displacement vector. Okay. What else can I illustrated for you the displacement vector? Now we have to talk about something else, right? Now we have to talk about the average velocity. And by the way, since speed is a scalar, we do not need to have it here, right? We're dealing just with vectorial quantities. Now we have, here you go, average velocity vector, average velocity. And how do we define the average velocity vector? We define as being AVG. And let's not forget, I gotta put the arrow first, right? Here you go, vector AVG is going to be just like we do in one-dimensional motion. It's going to be delta R over delta T, right? And notice that because we have a scalar quantity right in here, we can say that the average velocity vector is parallel to the displacement vector, right? Notice that the average velocity vector is parallel to the displacement vector. And that's what I drew right in here. That's what I managed to draw right in here, but I want a different one, right? Okay, and I have to go. I'm going to write down oh yeah, this one here. Oops. Oh gosh. Oh, huh, doesn't like it. What a shame. How I'm going to display that? Okay, I'll have to spell it out. Okay, delta R, V V average parallel to delta R. I want to, vai demorar. Okay. Parallel to V average is parallel to delta R, and I can even draw another vector right here. I want to put them which is with different color, right? Like that. I'm gonna put the average velocity vector in green color as well. R. We do not need that anymore, right? And then we can now go to the next step. We can next step. Next step is the instantaneous velocity vector. Instantaneous velocity vector. Velocity vector. And let's not forget, just like we had before, the instantaneous velocity vector is going to be the limit of delta R, delta T, as delta T goes to 0. Okay, and how does it look like in that graph that you saw, right? Well, we do, in order to visualize how the instantaneous velocity vector looks like in this graph, all we have to do is to choose a point. Let's say I want to get the instantaneous velocity vector here at this point. Suppose that I want to get instantaneous velocity vector at this point, right? Let's see here. Yeah, right here. Suppose I want to get instantaneous velocity vector at this point. Okay, what do I do? I make this interval right in here is smaller and smaller. We initially had, this one here, right? I'm gonna take it out, take it out, take it out. We initially had this point right here, and then he go. Yeah, I don't want that. I want to put my suppose I want to get my instantaneous velocity at this point in between those 2 points. How do you get the instantaneous velocity? Okay, we do that limiting procedure that we did before, right? Initially, you get the delta R vector like that. We approach those 2 points. Well, erase that here now. We don't need that anymore. we get those 2 points closer and closer to our actual point, what am I doing? I'm making delta t between those 2 points go to 0. That's what I'm doing. Okay. When I do delta t goes, and when I do the delta t goes to 0, I'm also doing my delta r going to 0 as well. Okay. So I'm going to take it out. I don't need that. Okay. In the next step, make it closer and closer. Okay. And then as we exercise this procedure, right? What do we end up discovering? We end up discovering as those 2 points come closer and closer to this other point where I want to calculate my instantaneous velocity, I notice one important thing. I notice that my delta r position vector tends to become closer and closer to a tangent to the path. Okay? That's why I'm doing this exercise here. Let's write that down. Okay. Notice that as we make delta t, notice that as we make delta t goes to 0, comma, delta r also does. Delta r also goes to 0. In this process, we realize that the delta r vector tends to get tangent, tends to become, right? To become tangent to the curve, to the path of the object at the point in question. Okay? Consequently, the instantaneous velocity vector will always be tangent to the path. Okay, we do not have a parallel to that in one-dimensional motion, right? So that's new information. Okay. In other words, the instantaneous velocity vector is always tangent to the path of the object. If I'm going to illustrate that, here you go. I'm going to copy that and place like that. Okay, I'm going to take out all those things here, and I'm going to draw my instantaneous velocity at this point right in here. Instantaneous velocity, vector velocity at this point here is going to look just like that. Okay, similarly, and I'm going to shorten a little bit so I can put the vector, the tail of the vector, exactly at the position where I want to illustrate the point for the instantaneous velocity. Elsewhere, like here, the instantaneous velocity vector is going to be like that. Okay, and in another point, we go right in here. It's going to be like that, and so on. This exercise only tells you what is the direction of the vector velocity. It doesn't tell you what is the magnitude of this vector velocity, okay? So here you go. And I'm going to get this guy here. Here's gonna be my instantaneous velocity vector 1. The other one is going to be my instantaneous velocity vector 2. The other one is going to be my instantaneous velocity vector 3, and so on. Okay? 2:36 is almost a break. Time for a break. Let's see if I have that here. Here you go. I'm doing the delta t going to 0, right? Here you go. And that's the instantaneous velocity, which I have already. Okay. 2:36. I think that we can now stop here, take a little break, and let's see if I have to write anything else. Instantaneous, always tangent to the path of the object. The path that the object is taking. That the object is taking. Whether it is in the 2D space or 3D space. Okay. Let's see. Yeah, let's take a break now. 2:37, and next time we continue that with the average acceleration vector, right? That is going to be 10:37. Any question about that? AM 2, 10:52. Okay. Break. There's no questions, so I'll see you in 15 minutes. See you soon. Bye-bye. Stop sharing. Recording. Okay, I'm back here. And now I want to know who doesn't have a group, right? A lab group.
I don't have a lab group.
Yeah, send your names to the chat window, please.
Okay.
While we are at that, let's see. Just one student doesn't have a lab group? Evelyn, okay. Evelyn Ayala doesn't have a group. Okay, so. Oh, Trin, okay. Okay, so why don't you make a group with Evelyn, okay? Evelyn and Trin. Let's see here. You are going to be group number, Evelyn, group number 13. So, Trin, did you manage to register to the course? Are you having access to Canvas and everything? Oh, okay. No, I'm asking Trin. Let me see here. Evelyn, let's see. So let me see what's going on here. Isabella, do you have a group, Isabella?
No, I don't have a group.
Okay, so 3 students doesn't have a group, right? Okay, so let me get organized here. Okay, Isabella. Isabella Cisneros, right? Okay, so I'm gonna put you on group number 13, Isabella Cisneros. The other student is Evelyn Ayala, 13, and then we have Trin Hernandez. Trin. 24, and we go 13. Okay, exchange contact information among yourselves, okay? Trin, Isabella, and Isabella Cisnero, and Evelyn. Just for the sake of see if everybody's here, right? Let's see. Eric, are you there, Eric? Eric Alcala? I'll take attendance again, right? Just to make sure everybody has a group. Is Eric Ayala, Eric Alcala there?
Yes, here.
Okay, thank you. Next, Edith Alexandrian. I don't see Edith here. Okay. So, like I said, Trian, Evelyn, and Isabella get in touch with each other and exchange contact information. Okay, you can do that through chat right now since Trian doesn't have access to Canvas yet. Jawairia Ali. Jawaira is here, right? And Jawaira has a group number 2. Evelyn is here. Let's see, Ben Bendoy. Are you there, Ben? Okay, thank you. And Ben has a group. Let's see, Melissa Bedola. Are you there, Melissa? I don't see Melissa here. Next, Miesia. Miesia Bragg. I don't see Miesia either. Queen Castaneda.
Here.
Thank you. Simone Cato Jack. I don't see Simone here. Next, Emily Serna.
Here.
Thank you. Emily has a group, right? Cecilia Chavez. I don't see Cecilia here. Next is Isabella Cisnero.
I'm here.
Okay, you already have a group, right, Isabella?
Yes, with Evelyn and Trin.
Okay. Group 12. Next, Jacob Contreras. I don't see Jacob here either. And Delisha Dry.
I'm here.
Okay, you have a group, right, Delisha? Gabriela Edwards.
Here.
Okay, you're here. Okay, you have a group too. Angelica Franco. Let's see,
Here.
Angelica has a group, right?
Oh wait, I'm here.
Okay, good. You have a group, right, Angelica?
Yeah, with Princess.
With Princess, right? Okay, good. Princess, are you there?
I am here.
Okay. Next is Carlo Gallardo.
Here.
Okay, you have a group too. Brandon Guerrero.
Here.
Okay. You have a group. Sydney Hill. I don't see Sydney here. Okay, next, Arturo Lagunas. I think Arturo dropped, right? Lagunas. No, didn't drop yet. Okay. But it's not here. Janie Maldonado.
I'm here.
Okay, you're group number 8, right? Isabel Medina. We don't see Isabel. Medina. Next, Kimberly Morales.
Here.
Okay, you're in group number 9. Montserrat Morales.
I'm here.
Okay, thank you. You also have a group. Someone is trying to. Okay, come in. Isabel Medina. Okay. Hello, Isabel. Are you there?
I'm here, Professor.
Okay, good. So you have a group, right? Let's go, Arwa. Arwa Paris.
I'm here.
Okay. Catherine Perez. I don't see Catherine here. Okay, let's go for the next one. Nicolas Rivera. Nicolas is here, right? Nicolas has a group. Let's see, Elizabeth Saldana.
Here.
Okay, you have a group. Do you have a group, Elizabeth? You don't have a group?
No.
Ah, okay.
No.
So let me put that. Okay, so let's do the following. Let me put here a note in your name, and then I will. Elizabeth Saldana. Let's see, and then I'll fit you into a group soon. Okay. So
Okay, thank you.
Jason Sevillon, are you there?
Yes, I'm here.
Okay, you have a group. Armon.
I'm here.
Okay, you also have a group. Jania Tapia. Let's see, there's no Jania here. Next is Juan Torres Arellano. Juan Torres Arellano has a group. Okay, thank you. And Trin Hernandez. Okay, so let me see here. I'm going to do the following. Search name. I'm gonna put a group. Good. So we're going to do the following. Okay, I want let's do the following. Trin, join. Sorry to change it now, but why don't you join Elizabeth instead? Okay, Elizabeth Saldanha, since she doesn't have a group, I'll put you in group 14. Okay, together with Elizabeth. Okay, exchange your contact information, Elizabeth. Exchange your contact information with Trin. Trin, the student doesn't have access to Canvas. So, okay, so let's do the following. So Trin and Elizabeth in group 14, and I'm going to give you the information for group 13 and search. Let's see, blah, 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 blah. Data sort, group number, like that. Good. Okay. And let me give you your links, group 13 and 14. Google Drive. Group. Let's see here. Name, share, copy link, share, editor, done. Okay, group 13. Group 13 are Evelyn Ayala and Isabella Cisnero. Evelyn Ayala. Okay, Evelyn, that's your link for your group folder. Let's see how, I'm typing the wrong place. Here you go. Make sure your link works. Evelyn, group 13, and now Isabella. Let's take a look at Isabella here. Isabella Saldanha. No, Isabella Cisnero. Okay. That's your link for group number 13, Isabella. When you access that link, make sure you see this window, okay? When you click this link, you're supposed to see this, this window with group 13 here at the top, okay? And I will provide you also with some documents for you to work today. Let's see now. Let's worry about group 14 now. Download, share, copy link. Group 14. Group 14 is going to be Elizabeth Saldanha and Trin. Here you go, Elizabeth. and 3. So, okay, so Trina, I sent you the link for your group folder. Student. Did you get the link, Trina? Okay, good. Thank you. Okay, so let's see. I gotta upload the group spreadsheet for you two folks. Those, okay. And now I'm going to upload group 13. Here you go. I uploaded your spreadsheet that you're going to use for this lab, group 13. Make sure you download this spreadsheet to your hard drive, to your computer hard drive. And now group 14. Okay, group 14, you have your spreadsheet as well. So if you open in there, you see the spreadsheet there, right? Group 14, if you, yeah, you also have your spreadsheet there. Okay. Make sure we will be using this spreadsheet for lab number 1. Note see that we have all those labs here, 2, 3, 4, 5, 6, 7. You may delete them, okay? Please delete them. You're not going to use that. Just lab 1, just keep lab 1. Okay, so we are done with groups 13 and 14 are set. Anybody else doesn't have a group? I guess everybody has a group now, right? And we're going to pick up where we stopped last time. What the last time? Last time we plotted the lab 1. Let's write that down here. Lab 1 continuation. Lab 01 continuation. Page break. Last time we plotted M along the y-axis and V along the x-axis for the ruler, right? That's what we did last time. I'm just gonna repeat what we did last time so you can refresh your memory. Okay, so let's see. Here you go. So first thing, for those who missed, right? You gotta get the density of steel from the internet. There's a range of density for the steel, or density values for the steel, and just take the average value. Okay, so you go to the internet, get look for the type there, density of the steel, and you're gonna get a range of values. Take the average value. Okay, so I'm gonna document here. 1. Look in the internet. What is the density of steel? You should get a range of values. Density of steel, by the way, in kilogram per cubic meter, right? In kilogram per cubic meter. Should be, remember, always should be in the main SI figures. You should get a range of values. We will take the average of this range and type this value in cell. What's the cell number? Cell is K16. Cell K16. Okay? Type this value in cell K16 in Excel. Okay? Look the value of the density of steel in the internet. Should get a range of values, take the average of this range and type in this value in and type the average, right? In cells K16 in Excel. Next, plot M along the y-axis and V for the ruler along the x-axis, right? That's where we stopped, right? So we did other things too. So what you're going to do, you're going to highlight the mass that you have here. And remember, right, what we have here, we have the diameter and the volume of 6 different spheres. That's what we have. What you have right in here is the actual measurements, including the mass that other students did that for me in the past. And what you have right in here are just results for the volume. Volume is not a measurement. Volume is a result that you obtain from the measurements of the diameter of the sphere. I took 3 different diameters, right? I took the measurement of the diameter of the sphere with a ruler, 6 sets of data. I took the measurement of the diameter of the ruler of the spheres with a vernier caliper, which is that instrument that I showed to you last time. And I also took the measurement of the diameter of the spheres, of each of those spheres, using the micrometer. Where is my stuff here? Let's see, I want to show you, just to remind you. Here is the vernier caliper, the very important instrument of measuring instrument. It's not just a ruler that we use, but we use this device as well, which is a fancy ruler. Okay, and I'm going to tell you the difference between this device and the ruler. And here is the micrometer, my micrometer. Here is my personal micrometer that I bought during a project that I managed to be awarded. I bought both the ruler, both the micrometer and the vernier caliper in 2003. Those are not digital devices. Those are mechanical devices. The vernier caliper, the digital vernier caliper that I had, you know, it's broken already. I had to throw it away. I bought it much later than this vernier caliper here, and this vernier caliper is still working. But like I said, the digital vernier caliper that I used to have, I have to throw it away because it broke down. Okay. And what you're going to do? Okay, so plot the mass versus the volume using the ruler. Most of you have already done. It's just group 13 and 14 who didn't do. Okay. How do you plot it? You highlight the mass. You hold the control key and highlight the volume value for the ruler. That's one of the first things that we do. Insert, right? Go to chart and plot. And you should get something like that. It's more or less a straight line, okay? So group 13 and 14, make sure you get that. That's your first graph they're gonna plot for this lab. There are two more graphs. Don't forget to, put the axis labels, right? And I don't like the title there. You have click, what else do we have to do? Click one of the data points of the graph, right, see them, all of them highlighted. Once you have it highlighted, right click, add trend line. And automatically you're gonna get a linear trend line. Let's see. Let me erase it again. Oh yeah, here you go. We're back. See this pane here on the right side? Once you get this pane here on the right side, you click display equation on chart, display R-square value on chart. And you should get this equation here at the top and the R-square value. In this case, 0.9927. Okay. So plot M, what else? Okay. Click one of the data points. They should all become highlighted. They should all become highlighted. Highlighted. Okay. Right click one of the data points. Okay. C, highlight, add trend line, right? Add trend line in the drop-down menu. Let's see if that's what I said here. When I repeat that all over again, just to make sure that my instructions are correct. And by the way, those instructions are in the syllabus, okay? Click one of the data points. All the data points become highlighted. Right click the data points. You have a drop down menu, add trend line. See that? Add trend line. Okay, right click one of the data points. A drop down menu should show up. Highlight add trend line drop down menu. And a pane should appear in the right side of the graph. Okay. Right side of the graph. And should be clicked linear. It's already pre-selected for you. You don't have to worry about that. That's why you have a linear line here. click display equation on chart, click R² value on chart. Okay. Click on the right, on the pane on the right side. Click display equation on the chart, right? Check, right click, no, check right side, check the box, check the box, display equation on chart, display equation on chart, and the other box is display R² value on chart. And the box display R² value on chart. Display. You're going to use those two pieces of information, R² value on chart. You're going to use, okay? Next, 3. Read the slope on the slope in the regression equation, right? In the regression equation, and log it in cell. Let's see what the cell is. The cell is this one right in here at the bottom, the last table. Cell K51. K51. My slope is what? My slope is 8,092.5. 8,092.5. That's my slope. But I didn't log the theoretical value of the density. Let's take a look at the theoretical value of the density, right? I did all of that last time, remember? Theoretical density of steel. Here you go. Anywhere between 7,700 to 80,000. 8,000. Take the average value of those two, right? Average 7,750, 8050. Average 5750, 8050. And that's what I get. I want to display it in a more user-friendly fashion. So I'm going to right-click, format cell, number instead of scientific notation. I'm going to display it as a numeric notation, 7,900. So note C that my slope is very close to the density of steel that I got from the internet. That's no coincidence. Okay, that's no coincidence. And when I log my density here, I also get the percentage difference of between those two values. And I'm going to, again, I'm going to put that in a more user-friendly format again. Number, right? Here you go. So I'm getting 2% difference between my experimental value, which is the experimental value is this one, and let's say the theoretical value that displayed in the internet. 2% difference only. You may get, depending on the data that you get, you may get up to 10% difference, maybe 15% difference. It's okay. Okay? And then what are you gonna do? Let's see. That's K51, right? K51. I'm read the slope in the and log it in cell K51. Check the percentage difference value. Okay. Then what do we have to do? Repeat steps 2 through 3 2 and 3 for the vernier caliper and the micrometer. Okay, so going back there, writing here, there's a little trick that I mentioned to you. Don't forget to put, label the x-axis, right? Let me write that down too. Add the labels for the x and y axis. Symbol for volume with its unit, symbols for volume and mass with their respective units. Okay? Symbol for volume and mass with their respective units. So repeat steps 2 and 3 for the vernier caliper and the micrometer. I'm gonna do that. Here you go. Let's see, mass, right? And then now we are going to get the volume as obtained using the vernier caliper. So what do? Highlight the mass, click Control key, right? The Control key, and then you highlight those values here for the volume of the vernier caliper. Insert, chart, scatter plot. Here you go. That's my second graph. Repeat what you did. Click, highlight every one. Click on one of the data points, highlight every one. Right click, add trend line. The trend line that should show is the linear one. Is the one that you use most of the time. Display equation on chart. Display R-square value on chart. Okay, and now I'm going to do the labels of the axis, right? The labels of the axis. Click the graph, add chart element, X title. X title, primary horizontal. So he make a box here for you to type. And then repeat for the primary vertical. Yeah, and you put another box here for you to type. The volume, right? The x-axis is the volume. And then you type V and you put M cube. Put M cube here. Since the cube must be superscript, you can highlight the number 3, right click it, font, superscript. And now you have your volume nicely displayed with the proper unit, which is the cubic meter. But this volume is still too small for me to read, okay? Let's make it larger. Not only larger, but let's boldface it to make it easier and nicer for us to see. Okay, I want to display it. Let's display it. Volume, yeah. Looks like 18 is fine. If you have enough time, also italicize the volume, italicize the M to look nicely. And you gotta work on these numbers along the x-axis as well, okay? So 0, 1, 2, 3, 4, 5, 6 times 10 to minus 6 cubic meters. Those fonts are too small too. They're only size 9. Let's make it larger and let's boldface it too to make it easier to see it. Here you go, 9. I'm going to put it on size, let's put size 14. Yeah, size 14 is good. Okay, this one here is size 18. Yeah, size 18 for the label, size 14 for the axis. Now let's take a look at this axis here. Do you see that? 0, half, point 0.300, right? 0.500, 100, 200, 200, 300, 300. Okay, in this case here, don't see that the labels are repeating. The labels are repeating because we do not have enough decimal places here. That's why they are repeating like that. So you can do two things, you know? You can either eliminate, some of the labels here, and it's easy to do that. Just double click here and, click on this one, axis options. Okay, maximum axis options. Let's see here. Oh yeah, units. You put a major unit, 0.001. If you put 0.00, let's see here, minor, yeah, put 0.01. Let's see. Yeah, good. And now it populates with less numbers, right? Because I increase the distance between. It's okay to do that. And let's increase the size as well. And to make it nicely visible, boldface, let's boldface it. Let's see how we boldface it. Font, regular, boldface. The size was 14 that we used, right? And now, yeah, now we have it. 0, 100, 200, 300, 400, 500. That's what goes here in the vertical direction. What goes in the vertical direction is going to be the mass, right? Mass. And just like before, we type big M for the mass, lowercase kilogram. I'm going to boldface it and make it what? 18 size, right? I had here 18 as well. Make sure you make the size the same, the size that you have here. Make sure the size here is the same as the size this one is, okay? And the size that this one is the same as the size of this one. Oh yeah, you're supposed to follow along. Yeah, you don't do any calculations, okay? The spreadsheet already doing all the calculations for you. The spreadsheet is already programmed to do all the calculations for you, okay? And what else do we need to do? We're gonna get this slope, right? 7937, and we are going to log there in the last table, right here for the vernier caliper. Oh, it didn't copy. Let's try it again. Let's try it again. Sometimes for some reason it doesn't copy. And this is for the vernier caliper. I'm going to try to copy that. Here you go, copy. It's not copying. Exit, font, delete. Doesn't have a choice here for copy. Let's see. Let me do the keystroke. Let's see if it copies. I did the keystroke here. If it doesn't copy, just type 79. Just type the value that you have. Here you go, 7937. Okay. Oh, see that? That's very good, right? Almost 0%. It's not exactly 0%, right? It is a little bit more than 0%. Let me change the font and put 2 decimal places here. Yeah, it's not 0%. It's 0.47%. So the vernier caliper measurements ended up better than the ruler measurements. Okay, and plot, you're gonna plot, and then you plot the last graph. Last graph is we're gonna be doing that the entire semester. We're gonna be plotting different graphs and doing exactly what I'm doing, okay? Here you go, highlight the mass and the volume for the micrometer, insert, chart, okay, linear, add trend line, display equation chart. I'm not gonna put the axis, okay? Make sure you do put the axis in your spreadsheet because I correct your spreadsheet according to all of that. Okay? It may look like lots of work, but that's what we do in real life. When you want to publish something, where I write reports for agencies that are funding my work, I do all of that stuff. Okay, and even more than that. Now 7947, very close to 7947, and we're gonna get 0.59%. Okay. Any questions? Let's see, what time is that? I think it's time to get a break, right? 11:41. Let's take a little break now. And then break from 11:41 a.m. to 15 minutes, 11:56 a.m. Right? And then we go for another 50 minutes. After we come back, we go for another 50 minutes. Here you go. 11:42. I took so long. Let's put 57. One more minute of break here. Any questions? We have 20 students here. Let me take a look at my roster. 24, okay. Okay, so I'll see you in 15 minutes. Okay. I am back here. Okay. Everybody has been able, so at this point in time, you should have all the three graphs there plotted, nicely plotted with the axis labeled and everything, okay? And don't forget, when I correct your stuff, I'll be correcting it according to how nice you produce those graphs. And what we have to do next, okay? So I usually do the following, during those labs, I usually do the following. The first thing I do is plot the graphs. That's the first thing I do, plot the graphs. That's the how do you say that? The script, right? The script for my labs, right? What the script for my labs? First, we plot the graph so you can see the results. Okay. Next, we log the value of the slope in one of the tables to get the percentage difference. Huh? Our labs have the following script. Okay, following script. First, we plot the graphs. Then we log the value of the slope and or intercept. Sometimes we also have the intercept also in one of the tables to get the percentage difference. From this percentage difference, you can infer how good your data is, okay? Next, we fill up the units of the parameters, right? Let's take a look. Here goes spreadsheet right here. Okay, so here go. The unit here for the density of the steel is already I already wrote that down for you. Okay, some of the units already write that down for you. Other ones you have to write that by yourself. See, the diameter of the ruler is in meter, right? So the diameter for the vernier caliper is going to be meter as well. And micrometer is going to be meter as well, right? To find out the unit for the volume, you have to look at the equation, right? That I printed here for you. 4/3 of pi r cubed, right? If you, what I have here is not the radius, right? What I have here is the diameter. So in order to get the radius, I have to get the diameter divided by 2. And that's what this equation is all about. So you go ahead and look at the equation, do dimensional analysis, and you get what your unit is going to be, right? The volume unit for the volume is going to be cubic meters. Cubic meters here, cubic meters here, and cubic meters here, okay? There is no units for you to fill in this table. Okay, there's no unit yet for you to fill in this table, but then there is a unit for you to fill here in this last table. Do you see here units? What's the unit of the slope? Okay, you gotta type the unit of the slope here. Don't forget that the slope represents the density, right? So you go ahead, put the unit for the density right in here. And this last one is the percentage difference. Okay, and you have to look at the equation to find out what is the unit. Because we have this number 100 here, you see that? The percentage difference. Because I put this 100 here, the unit for these three quantities here, these three quantities, is going to be the percentage sign. It's stricken out, right? Let's fix that. Format cell font. Where's the font? Do you see that? There's a strike, a stricken sign. Let me see if I can fix that font. It goes to font. Oh yeah, it strikes through. Uncheck strikes through. Hopefully, I believe everybody has this problem. Okay? And then you gotta put the unit for the density here. Okay, so that's part. Next, fill up the units of the parameters. For what you do next. Next, you display the proper number of significant figures. Significant figures. We didn't cover significant figures yet, okay? I want to cover that with you. I'm gonna tell you how you do that. Okay. And then how do you first you have to know the number of significant figures, okay? Of each of your measurements. Significant figures. Here you go. Significant figures of your measurement and significant figures of your results. Of your results. Okay. And once you know the significant figures, you are going to have to adjust the format of those numbers that are displayed here, right? Oh, here goes. The diameter, right? Sometimes you're going to leave in scientific format, but sometimes you have to put that in, most of the time you have to put those measurements here in numeric format. Okay, and so let's cover the significant figures now, okay? Let's cover the significant figures now. There is one, let's see, and what else do we have to do? Fill up the table for the CL, okay? Fill up the table for, let's say, for A, more than one, okay? It should be the second table. No, it's the third table, this table here. That will be the third table, okay? Fill up the third table. Fill up the third table. Let me just write that down and we are going to talk about significant figures, okay? A, number of data points, N, okay? Regression equation. Regression equation, see that? That should, the M stands for the mass. So I want you to type the regression equation here, here, and here, right? For the ruler, for the vernier caliper, and for the micrometer. And the R square, regression equation, C, the R square value for each graph, and D, the lower and upper bounds of CL. And remember that we covered that as well, right? I can go back to that, but let's talk about the significant figures first. Okay. Okay, so when you make a measurement with a given instrument, comma, it is incorrect to display, let's say, an instrument. You must display the right numbers of figures of your measurement and then the results, okay? Let's talk about before we talk about the results, we have to talk about the measurements. Measurements and then the results, okay? Now, let's talk about the measurement first. Measurement. The number of sig figs of your measurement, comma, depends on the instrument that depend on the measuring instrument, you are using. Okay? In this class, we will use the resolution of the instrument to determine the right number of sig figs, okay? We will use the resolution of your instrument to determine what is the resolution, okay? Then you gotta ask, what is the resolution of an instrument? What is the resolution of an instrument, okay? That's what I should be asking. Answer? A question, right? Question. What's the resolution? Answer. It is the smallest division in the instrument, okay? It goes from instrument to instrument. In the case of the ruler that everybody's familiar with, in the case of the ruler, the smallest division is the millimeter, okay? 1 millimeter is 1 millimeter. 1 millimeter. Consequently, its resolution in meters should be resolution in the other units should be, okay, here you go, 1 millimeter is equal to 0.1 centimeters, which, by the way, is equal to 0.001 meters, okay? In meters, is we have to divide the 1 millimeter by 1,000 to get the resolution of the instrument, okay? So now we are going to apply this rule here that you see to display the proper number of significant figures in your measurements, okay? So what does it mean? You know, what does it mean? What does it mean? Okay, it means that your measurement must be displayed in the following way. You go x dot x meter. That's what it means. You cannot add a force. You will be incorrect to add a fourth decimal place here, okay? Make sense? It would be incorrect to add a fourth decimal place because your instrument cannot tell you for sure what this value is, okay? So let's go back to our table, right? Right here. Let's take a look at the ruler. Here you go. We're looking at the ruler only, and then later on I'm going to tell you about the vernier caliper. Hopefully we have enough time to do everything today. If not, we're going to have to meet again on this lab next week, okay? Any questions so far? No questions? Here you go. If you click this cell here, you can read the number that was typed there. And this number is 0.019. Remember that I told you you have to display only up to the third decimal place in meter, right? So what do we do? Here you go. Click the cell, right-click the cell, and go to Format Cell. Format Cell, you go to the tab Number, and you click. Right now it's clicked on Scientific, right? So you want to change the format from Scientific to numeric format, okay? You change to numeric format and you add 3 decimal places for your number. And now you display it properly. Here's a measurement done with a ruler. And that's the proper way of displaying or reporting the measurement done by the ruler. Okay? And then you can do for the rest too. This one here you go. 0.022, right? Right click, format, number, 1, 2, 3, and boom. We have displayed properly. And now, all those measurements that you see here, by the way, they will all have the same number of decimal places, okay? Because they will have all the same number of decimal places, you don't need to do one by one. You can do everything all together. Highlight every one, right-click, format cell, number, 1, 2, 3 decimal places. And now I'm displaying the measurements with the proper number of significant figures. Okay? Don't forget, the rules for measurement is different. The rule for the number of significant figures for measurement is different than the rule for the number of significant figures for results. Let's see, someone here is trying to come in. No. Okay. Okay. Now, what about the vernier caliper? The vernier caliper, because it's a fancier instrument, it has a better resolution than the ruler. It is possible to measure up to the tenths of a millimeter with the vernier caliper. And what allows you to do that is what we call the vernier scale that we have here in this device. Okay, let's see if I can display that for you. Let's see here. I used to have a slide for that illustration. Maybe it's here. Oh yeah, here you go, right in here. Yeah. Let me close this one. Feels so good when we get it right. Here you go. Okay, that's how the vernier caliper is built. Okay, you have this is a very simple illustration. Okay, I want to make it as simple as possible. So it has a regular ruler, which is this main ruler here. Let me show you my actual vernier caliper. Okay, see here, this part is just a regular ruler. This part of the vernier caliper is just a regular ruler. But then we have this fancy ruler that goes down right in here. This one here is called the vernier scale, the vernier scale. Okay, and I put my vernier scale here. But right now is covered. Okay, I'm going to uncover it. The vernier scale is graduated from 0 to 10. Okay. Yeah. Like that. If this zero here of the vernier scale is lined up with the 0 of the main ruler, the 10 here, should be lined up with the other one as well. Okay? See? This one is lined up. This one must be lined up as well. Okay? Okay? It is because of this vernier scale that we can make measurements up to a tenth of a millimeter. Okay? But before we do that, let me just cover this scale here first. And let's learn how to make measurements with this vernier caliper using just the regular ruler, right? Here you go. I want to, here you go. Group everything, okay? So in order to make a measurement with the vernier scale, with the vernier caliper, we have to open those two jaws, just like I did here, right? And fit my object. Let's say I want to get the diameter of this laser pen, right? I clamp it, okay? I clamp it, and did I do well? Let's see. Yeah. And just take a reading. Suppose that I put, let's see, I'm gonna use this one here as an example, okay? One, two, three, five, 7. I'm gonna get that as an example. Okay, I get this object. I'm measuring the diameter of this object. Okay, is slightly larger than, okay, now we got it. So what do? You look at the zero here in the vernier scale to find out the diameter of this object. For now, I'm just uncovering the vernier scale. So this vernier caliper is working just like a regular ruler. So at this point here, you can say that's around 7 millimeters, okay? 7 millimeters. But suppose that the object were slightly larger than that, okay? Like that. I'm going to increase the size of this object. Here you go. Now you can see that this object is going to be, here you go. Let's zoom in, right? 7 millimeters plus something else. See that? Plus something else. We cannot tell by the naked eye what this plus something else is. We can have an estimate, okay? If I were to estimate this something else, I would say that would be 7 millimeters, 7.4 millimeters if I were to estimate. But the nice thing about the vernier caliper is that it has that vernier scale that allows you to tell exactly what this something is all about. Okay, and what do you do? How do you do to make a measurement of that, right? You have to line up one of those lines that you see here. Gotta see which one lines up with the one at the top, okay? Look what's happening. You know, as I move forward here in this vernier scale, this line starts to get closer and closer to its corresponding upper line, okay? See, this one is closer, closer, closer. It looks like until we reach this other one right in here, that almost, you know, that's very closely aligned with the other one. If you go to the next one, you can see that it's already over, you know, jumped, right? It's too much to the left. And then the other ones keep on going further and further away. So from this measurement here, I can tell you that this device is measuring 7.4 millimeters just because of the vernier scale. Okay? So if the ruler, you get the idea of the vernier scale? If the ruler has a 0.001 meter resolution, comma, here you go, 1 millimeter, which is equal to 0.1 centimeter, which is equal to 0.001 meter resolution, comma, the vernier caliper has a better resolution, which is 0.1 millimeters, right? Which is 0.01 centimeter, which is 0.0121 meter, 1/10 of a millimeter. If here I have 2 zeros, here I have 3 zeros, right? I can even start building up a table for you. Here you go, table, insert, table, 1, 2, 3, instrument, okay, instrument, resolution. You wanna put that in meter. Ruler, vernier caliper, and micrometer. Here is going to be 0.001, 0001, and guess what's going to be the micrometer? The resolution of the vernier caliper is 10 times better than the resolution of the ruler. And guess what's going to be the resolution of the micrometer compared to the resolution of the vernier caliper? Is going to be 1, 2, 3, 4, 10 times better than the other, and 100 times better than the resolution of the ruler. Okay? that how those three different instruments compare. So if a measurement, right, by the ruler must be displayed up to the third decimal place, right? I'm gonna put it here. Here you go. 1, 2, 3. A measurement with the vernier caliper must be displayed up to the 4 decimal place. 1, 2, 3, 4. And a measurement with the micrometer should be displayed up to the 5th decimal place. Okay? Can you remember that? And what allows the micrometer to have such a fine resolution has to do with the device that we have right in here. Okay? And notice that for the micrometer has this radial division in 50 different divisions, okay? I can even get a simulation for you to look at it. Let's see if I can get it. Well, you know what? Doesn't matter. Micrometer simulator. Virtual micrometer in hundreds of millimeters, okay? Simulators. Here you go. With the virtual micrometer. You see how the micrometer is built? It has a regular ruler, which is this one here running along the horizontal direction. Let me see. Oh, right in here. That's what I want. Stop it. Stop it. Yeah, here you go. I'm going to, I'm going to open completely my micrometer, okay? Those micrometers, they usually can measure up to 1 inch, 25 millimeters. That's the price to pay for such a high resolution instrument, for an instrument such a high resolution, okay? So here is my regular ruler. See that? The ruler has its scale. The vernier caliper has a ruler scale as well. And the micrometer also has a ruler scale, which is 1 millimeter resolution only. And below here, we have half millimeter, 0, half millimeter, 1 millimeter, 1.5 millimeter, and so on. What really provides the very high resolution of the micrometer is this radial scale that you see right in here. See that? It has 50 divisions. See that? 45, 46, 47, 48, 49, 50. Okay? And one full rotation of this radial scale correspond to half of a millimeter displacement, okay? So half millimeter, 50 divisions. 1 division, 100 of a millimeter. We have been able to build something like that with current technology, okay? And then there are other micrometers out there that can go even further than that, okay? Those are the regular micrometers that we find out there. But if you add like a vernier scale, it's possible to do that. By the same token that the vernier caliper has a vernier scale, we could add too a vernier scale to this micrometer. My micrometer here has a vernier scale. And because of this Vernier scale, I can go one step higher in resolution. Instead of 100 of a millimeter, I can measure thousands of a millimeter. Okay, thousands of a millimeter, but we're going to stop here. Okay, the resolution that you're going to use for the micrometer for the rest of the semester is going to be 100 of a millimeter, or 0.00001 meter. Okay, let's see, someone is, okay, someone has a, I have to, okay, good. And now, oops. And now we can go ahead and display the proper number of significant figures for the vernier caliper. If the ruler is 3 decimal places in meter, for the vernier caliper is going to be 4 decimal places instead. Okay? Those measurements are very close to each other. See that? But because it has a higher, vernier caliper has a higher resolution, we can display this other decimal place here that the other one doesn't. Here you go. See zeros, you have to display the zero. In this case, the zero is a significant figure. Okay? 155, 121, 100. Okay? Let me write that down about the zero, okay? Any non-zero number is considered a significant figure, okay? However, the zero is considered a significant figure only if it is to the right of a significant figure. Okay, that's the rule that we use. Zeros to the left of the leftmost non-zero number are not considered significant. Okay, and now we can play a little bit with this one here. Here you go. How many? I want you to think. How many significant digits we have here? How many significant digits we have here? I want you to think about that. How many significant digits we have here? Okay? Remember what I said, right? Zeros to the left of the leftmost non-zero number are not significant. Okay? So here you go. Examples. 0.019, 2 significant digits. Okay? 0.010, 2 significant digits. Okay? I can even put another zero here in front of it. Still gonna be 2 significant digits, right? Still gonna be 2 significant digits. Right? And here you go. 0.100. Now we have 3 significant digits. Okay? Let's see. 1, 2, 3. 3 significant digits as well, and so on. Those are examples. And we're talking just about measurements, okay? We're not talking about results yet. 4:36, we have 15 more minutes to go. Let's see how how much we can cover until what? 12:50, right? Let's go to my spreadsheet here. Yeah. And then I gotta display the significant digits for the micrometer. If here we have 3 decimal places, 2 significant figures, 4 decimal places, 3 significant figures. For the micrometer, we are gonna have what? We're gonna have 5 decimal places. Okay, 5 decimal places. 5 decimal places, 4 significant digits. Okay. Okay, what else? Which other measurement we took? We took those measurements here, right? We took a measurement with the kilogram, in kilogram, the mass. And the number of significant figures here is going to depend on the scale that we used, okay? And I'm gonna tell you what the scale that we used. For the measurement of the mass, comma, we used a scale that has the following resolution. For the scale, 0.01 grams, okay? Okay, that's the resolution of my scale. Which, by the way, can be written down. Don't forget, we have to write it down in terms of the main SI units. 1, 2, 3, 1 kilogram. 10 to minus 5, right? 1, 2, 3, 4, 5. Yeah, 10 to minus 5. 10 to minus 5 kilograms. That's how we represent in scientific notation. Superscript. Okay. And now we go back to our table here. And we go ahead. We display my measurements with 5 decimal places. Let's count if it's 5 decimal places. Here you go. This one, right? Here you go. 1, 2, 3, 4, 5. Yeah, 5 decimal places. Right click, format cell, number. 1, 2, 3, 4, 5. All those measurements were made with the same device. Note that some measurements, even though it was made with the same device, some of the measurements have more significant figures than the others, right? Those here have 4 significant figures. Those here have only 3. Okay? Did you notice that? Okay. So that's what I want you to do. I want you to display those measurements with the proper number of significant figures. Go ahead, start working on that. Doesn't look like we'll be able to finish today, right? Ten more minutes to go. Let's see if we can finish today. At least the significant figures I'll try to finish today. Okay. So here you go, significant digits. Significant digits, okay. What the heck is that? Sig figs depend on the instrument you use, okay? measure significant figures of a measurement of a measurement. Depends on the instrument you use. And now let's talk about significant figures of a result. It also depends on the instrument you use. However, there is one additional rule to determine the number of sig figs. Okay? Okay, for instance, it depends on the instrument you use. Okay, let's put it this way. It depends on the instrument you use plus the equation you used to determine this result, okay? So it depends on those two. Depends on the instrument you use plus the equation used to determine the result. There is a rule, okay? There is a rule for multiplication and division. There is another rule for addition and subtraction, okay? In order to find out the number of significant digits of a given result, there will be a rule for multiplication and division, and there will be another rule for addition and subtraction. The rule for multiplication and division is simpler. The rule for multiplication and division is simpler. Okay? It's simpler. Then the rule for addition and then the rule for addition and subtraction. Okay? So let's concentrate on the rule for multiplication and division first. Okay? In the case of the volume, the equation is the following, right? Gonna get that. You have to know the equation that you are using to get your result. In the case for the volume, here you go. Volume, capital V, 4/3 of pi. Okay? I'm going to write that down in terms of the diameter. Capital D divided by 2, right? Capital D divided by 2 is radius, right? And then you gotta raise to the cube. That's how the equation for the volume is, right? Volume of the sphere, of course. When we, take that term from inside the parentheses, right? We get something like that. And we end up with 1/6 d cube, pi d cube. So 1/6 pi d cube is d times d times d, right? D times d times d, right? So it's a multiplication. You gotta use the rule of multiplication. What's the rule of multiplication? Rule of multiplication division. And division for sig figs. You keep the least number of sig figs. You carry out, let's put here, you display the least number of sig figs in your final result. Okay. In this case, we have 3Ds, right? But 3Ds is they all have the same diameter, right? Same value, same number of significant digits. So let's go do an example here in my table. 4 more minutes to go. Here you go. Okay, so here you go. Here's the volume for the ruler. I got those values here. Note, see that my ruler, my measurement of the diameter has 2 significant digits, right? If you have 2 significant digits here, you must display 2 significant digits here as well, okay? All of them has 2 significant digits. Consequently, all of them should display 2 significant figures. Because this number is very small, less than 10 to minus 3, I recommend that you display it also in terms of scientific format, okay? And because we want 2 significant digits, we have to display 1 decimal place. And here you go. That's the right number of significant digits for the volume. Okay? And then you do the same for the vernier caliper. 3 significant digits. We gotta display 3 significant digits. Because again, the number is very small, less than 10 to minus 3. We are going to choose to display it in scientific format as well. Scientific format with 2 decimal places, 1, 2. And now we have 1, 2, 3, 1, 2, 3, 1, 2, blah, blah, blah. Okay? 3 significant digits here, 3 significant digits here. Finally, the last one, 4 significant digits. So we must also have 4 significant digits here, right? 4 significant digits in scientific format means that we must have 3 decimal places, like that. Did you get the idea? For now, all you need to know is the rule of significant figures for results results that use multiplication and division, okay? 449 right now. We didn't finish that. We are almost finished. So there's no lab report due yet. Next Wednesday, we are going to finish this lab 1 and start lab 2, okay? So you should expect to turn in this lab report 2 weeks from now. 2 weeks from now, okay? Any questions? 12:50 and okay, so I'll see you. If there's no questions, I see you next Monday. Okay? Bye-bye.
Thank
Thank
you,
you.
Professor. Have a nice day.
See you.
Professor, I have a question.
Yeah, go ahead.
I'm in group 8 and I uploaded my Excel sheet. Can you just check like if I did it correctly?
Yeah, you can upload your Excel spreadsheet to your group folder. And
Yes, I did.
what's your group? What's your group number again?
Group number 8?
8.
Yes.
Okay, group number 8. This one here. You
Yeah.
uploaded which one? This one here, right?
Yeah. Yes.
Yeah, make sure you keep the same title, okay?
The same title, so group 8?
Yeah. Same title, yeah. Make sure.
Okay.
And let me see what you did here. Download.
I know you said you don't like the titles, but I'll take them off.
Yeah, but there is one important another thing important. Okay, do not change the format of the spreadsheet. Okay, you need to keep everything that you did here in that original spreadsheet. Okay, you gotta
Okay.
everything that you did here, you have to keep in this format here. Do not change anything. Do not add do not add the lines. Do not add columns. I have a software that's gonna correct that, and the software needs to for the software properly correct your spreadsheet. You need to maintain
Um,
this format. Okay.
Okay, question. So, I download the file then as and open it in Excel
Uh-huh.
versus making my own Excel form, my own sheet, and just do it on top of the downloaded one.
Yeah. Uh-huh. Do that in download.
Okay.
Okay. Just like I'm
Okay.
doing here. See that? Just like I'm doing here. I didn't add, I didn't add lines. I didn't add the columns. I'm just working on the tables, on the original tables.
Okay.
Okay.
As I can go ahead and do that. I did write already like in the sheet that's already on there. I already like added the decimal points and stuff, but I'll go ahead and add the charts as well.
Yeah.
I'll just redo them because I
Yeah. Let's see. Where is your spreadsheet? Is that the one? Yeah,
yes.
that's the one. Okay. Yeah. Okay. So make sure you and do not change the format. And put your names here, right? Group number, blah blah blah. All right.
Okay. Do the at least do the charts look okay?
Let's see. Your group eight. Yeah, they look okay. 8,195. You have those 2 points, right? One, two, three, four. Why we have only 5 points here? Let's see where you have some 5 points only. Looks
Mm,
odd because those 2 points are very close to each other. That's why.
okay.
Okay, that's why. And yeah,
And then
that's
did you want to check the group one right there, the one next to it?
which group?
The file next to the one I uploaded. If I
You
did that
uploaded another
correctly.
file? You uploaded another file?
No, the original one. I
Oh, the original, this one here. Yeah,
yes.
let's see. Did you change it?
I just added like the information you wanted us to add.
Mhm. Okay, so here you go. Okay. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, now you have to work on that, okay?
Okay, on the other ones.
Here, let's work on this one. Did you fill it up? Yeah. Also change the format, right? Put that in numeric format.
Okay, same decimal points, right?
Yeah. So
Okay.
I can have a better reading of the data. Well, yeah, and then you gotta put your graphs here too, right? The graphs are not here.
Yes. Okay.
Okay.
I'll go ahead and add those in. Thank you.
Okay. That's it?
Yeah, that's it. Thank you so much.
Okay.
Have a great day.
Is it?
Bye.
Oi,